All right, welcome to my lecture on improper integrals. We're going to focus on what's called a type 1 improper integral. Okay, and I'm going to start off with an example, and then I'll give the definition of an improper integral. Okay, so an improper integral is going to have this form. Okay, integral from 1 to infinity of 1 over the square root of x dx. Okay, what makes this improper is this infinity symbol that I'm circling in blue. This is the improper part. Okay, and it's improper because we're only used to dealing with finite numbers here. Okay, and the question, if we draw 1 over the square root of x from 1 to infinity, this is roughly what its graph looks like. Okay, is going to be large when x is near 0. It'll tend towards infinity. And as x gets larger, this quantity, 1 over the square root of x, gets closer and closer to 0. So the question is, if I integrate from 1 to infinity, I'm accumulating all of this area. And although this output limits to 0 on the y value, the question is this a finite amount of area? Okay. An improper integral says, hey, I'm only used to dealing with finite quantities. So let's put in a finite quantity. Let's call it b. And then I'm going to take this limit as b goes to infinity here. Okay. And this is x to the minus 1/2 dx. And it says treat this part, what's in the parentheses there, as a finite quantity. And so we will, and treat it as a normal integral. So we'll go ahead and we'll anti-differentiate it. Okay, and this will be 2 times x to the positive 1/2 power, evaluated at 1 and b. Then it says, let's go ahead and plug in these limits of integration. Okay, so this will be 2 root of b minus 2 square root of 1. And this limit, as b goes to infinity, that equals infinity minus 2, which is infinity. So it turns out that the amount of area here of 1 over the square root of x from 1 to infinity is infinite. And when we have an infinite amount of area, we have what's called a divergent improper integral. So I'm going to go ahead and put this word down and say it's divergent. If it's finite, then we'd have what's called a convergent improper integral. And I'll give you an example of a convergent improper integral. Okay, it's going to be very similar to the one we just saw. I'm going to have this integral from 1 to infinity of 1 over x squared dx. This graph looks very similar to the one that's above. And again, what makes this improper is this infinity in the upper limit of integration. Okay, so we're going to replace this by a finite number and take the limit as that number goes to infinity. So this becomes this integral from 1 to b of 1 over x squared dx. The quantity that's inside this brackets is called a proper definite integral. Okay, and so we just treat that as a normal proper indefinite integral. Okay, and we'll get minus 1 over x, and we'll evaluate that at 1 and b. When we evaluate it, we're going to get this. Okay, and as b goes to infinity, this limits to 0, and that second number is 1. So this has a value of 1. The total area under this curve from 1 to infinity is finite. Okay, and so I'm going to label this as finite. And in particular, finite means this is less than infinity. Because this is less than infinity and finite, we say that this improper integral is convergent. Okay. Let me give you the definition of an improper integral of type 1. Okay. Okay. So case A is actually a case we haven't dealt with, but I'll give you another example. Okay. Oh, excuse me. Case A is an example we have done, and it says that this integral from a to infinity of f of x dx is equal to this limit as b goes to infinity of this integral from a to b of f of x dx. And if this is less than infinity, so maybe I shouldn't have written infinity, so I'll take that back. So if this, we'll call this limit L. If L is finite, i.e. less than infinity, then the improper integral is convergent. Now that's one scenario. Another scenario is L is infinite. Okay. Then the improper integral is divergent. Okay. So that's our classification for improper integrals. Of course, there's the synonymous one, okay, which is case B, and this is just that we have an integral from b to minus infinity of f of x dx, and we deal with this by taking this limit as a goes to minus infinity from a to b of f of x dx. Okay, and we say that this has a limit L. Again, if L is finite, then we say it converges. If L is infinite, we say it's divergent. And there's a scenario C here, which is that we have this integral from minus infinity to positive infinity of f of x dx. And the convention here is that we break these into two. minus infinity to a of f of x dx, and the integral from a to infinity of f of x dx. If both of these integrals in C converge, then we call the improper integral from minus infinity to infinity convergent. So in case C, if both integral from minus infinity to a of f of x dx and this integral from a to infinity of f of x dx are convergent. Okay, now each of these scenarios are treated in A and B, and the question is, do they have a finite amount of area in both improper integrals? If it's yes, then it's convergent, yes to both. If it's no to just one, then it's called divergent. And let's give an example of this. Example of case C. This would be this integral from minus infinity to infinity of 1 over 1 plus x squared dx. I'm going to break this into this integral from minus infinity to 0 of 1 over 1 plus x squared dx plus this integral from 0 to infinity of 1 over 1 plus x squared dx. Now let's deal with the improperness. Okay. Okay, so I'm going to have this limit as a goes to minus infinity. And let me write that correctly. So minus infinity of a to 0 of 1 over 1 plus x squared dx plus this limit as b goes to infinity of this integral from 0 to b of 1 over 1 plus x squared dx. And we're going to integrate each of these. This will be this limit as a goes to minus infinity. This is this arc tangent of x from a to 0 plus limit as b goes to infinity of this arc tangent of x from 0 to b. Well, this will be this limit as a goes to minus infinity of arc tangent of 0 minus this arc tangent of a. By the way, arc tangent of 0 is 0. Okay, plus the limit as b goes to infinity of this arc tangent of b minus the arc tangent of 0, which again is 0. Okay, well, the limit of the arc tangent of a as a goes to minus infinity, that is going to be minus pi halves. So minus and minus pi halves plus the arc tangent of b as b goes to infinity is going to be positive pi halves. So this is going to limit to be pi. And since this is less than infinity, this is called convergent. Okay? Thank you for joining me on Improper Integrals Part 1.